Alrighty, let's look at kinetic energy in this video. We know that translational kinetic energy, right, is 1/2 mv squared. Now you're like, what is translation? Okay, an object, if it's rolling down a plane, right? If we look at its motion, the fact that it moves to the side, that's called translation. Okay. The object also has a rotational motion, okay? So it also has rotational, okay? And so if an object rolls down the plane, it's going to have, without slipping, right, okay, it's going to have translational and rotational kinetic energy. Now, rotational kinetic energy is exactly the same thing. It's 1/2, not m, but I, not linear velocity, but angular velocity, right? So it's 1/2 angular inertia times angular velocity squared. Yeah. Okay, so that's one formula, and that's definitely in the data packet, right? And then there's other things you can do, because this is a pretty cool concept. In the translational world, we had work was force times distance, right? In the angular world, work is torque times theta, which brings up sort of an interesting thing, because of course torque is in meter newtons and theta is in radians, but radians aren't really a unit, right? So what's interesting is that when you multiply torque by angle and actually do angular work, you already have the units of joules, which is kind of cool. Torque and joules have the same units, okay? So let me just do an example problem here, and then I'll just do a whole bunch of examples, yeah, hopefully that'll help, right? Okay, so here's our example problem, right? A big cylinder rolls down a hill, right? So let's draw a picture of this. Okay, it's a cylinder rolling down the hill. So it starts at the top, right? Let's assume that it starts at rest, and at the bottom of the hill, it's got a velocity of 13.5 meters per second. Okay, and we know it's a cylinder, right? So its translational kinetic energy is actually pretty simple, right? That's just the kinetic energy that we're normally used to calculating. So that's 1/2 mv squared, right? So I'm going to go 1/2 23.7. This is a heavy thing, times 13.5 squared, and that kinetic energy is, let's figure it out. 0.5 times 23.7 times 13.5 squared. Well, that's 2159.6625 approximately joules, right? That's kind of a joke. I'm trying to be funny here. All right. Now, rotational kinetic energy is harder to do, right? So EK rot, okay, is 1/2 I omega squared, right? Well, we don't know I and we don't know omega, but we can figure them out, right? So let's do it. Okay, so let's see. I is, sounds like bad grammar, it's a cylinder, right? So I is 1/2 mr squared, right? It's 1/2 because of it's a cylinder. Okay, so that's going to be 1/2 times 23.7 times our radius is 0.45 squared. Okay, so here we go. Are you ready? 0.5 times 23.7 times 0.45 squared. That's 2.399625 kilogram meters squared, right? And then our omega is just V divided by R. Right, so that's the 13.5 that it's going, divided by the 0.45 meters that its radius is. So 13.5 divided by 0.45, somewhat unexpectedly, is exactly 30 radians per second, right? So now we're set. Now we can go 1/2, and then this guy 2.3996 right, times 30 squared. And we get the somewhat surprising result, 0.5 times that guy times 30 squared we get the somewhat surprising result that the kinetic energy is exactly half of this, 1079.83 joules, right? So you ask yourself, how is that possible, right? How is I got to box this guy up too there. Oops, I should cover that up. All right, why do I do that? So the question is, why is this exactly half of that? And the answer is that we would see that if we did the proper substitution. So let me just show you this, right? Rotational kinetic energy is 1/2 I omega squared. I is 1/2 mr squared, and omega is v over r. So if we substitute that, we get 1/2, not I, but 1/2 mr squared, right? And then we have v over r, the quantity squared, right? Well, now watch. Okay, if you square this, that's the same as v squared over r squared, right? Okay, r squared divided by r squared, well, the r's go away. The r didn't matter, right? And you end up with 1/2 times 1/2 times m times v squared, right? That's 1/4 mv squared, right? So the rotational kinetic energy is exactly half the translational kinetic energy, which is sort of interesting, right? That's where it comes from, right? Okay, so what's the total kinetic energy? Well, this is rocket science. That's 2159.7 plus 1079.8 is equal to, let's add those. I'm going to add them so precisely. Here we go. We got that guy plus that guy. And I get 3239, and that's joules, right? And then what's the height of the hill? Well, gee, at the top of the hill, it's got mgh. At the bottom of the hill, it's got this and this, right? So I'm going to say mgh before, right, turned into 3,239 joules of total energy, right? So we're going to just plug in numbers. 23.7 times 9.81 times whatever that height is got to equal 3,239.5, right? So now I have to divide by 23.7, divide by 9.81. And I've got 13.9, that height. Ta-da. There we go. And what's interesting is, of course, we could go the other way. If I told you the hill was 13.9 meters tall, I'm pretty sure we could be clever enough to figure out what the velocity is at the bottom of the hill. Okay, and I'll do that, but let's practice this concept first. Okay, so I'm going to do there's a bunch of example problems here.